Do well and you get worse. Do badly and you get better. Let's unravel the most common statistical illusion that has fooled the world. Introduction. Does praise really ruin people? The story begins decades ago, in a classroom of the Israeli Air Force. When the instructor taught this doctrine, a veteran flight instructor scoffed and pushed back head-on. Praise a trainee for a beautiful landing and his next flight gets worse. Harshly scold a trainee and his next one improves. That was his claim. So praise ruins people and punishment builds them. He said he'd seen it hundreds of times. This is an anecdote that the psychologist Daniel Kahneman called a moment of insight he would never forget. The awkward part is that the instructor wasn't lying. After praise, performance really did drop. After scolding, it really did rise. What was wrong wasn't the data but the story he attached to it. The true identity of what he saw was neither praise nor punishment, but regression to the mean. And this flight instructor's anecdote is only the tip of the iceberg. These stories, which look nothing alike, all flow from the same single piece of arithmetic. Not a conspiracy, not a jinx, not a curse. The moment we miss this simple fact, we start piling plausible myths of causation on top of perfectly ordinary chance. First, the story of the ordinary son of a tall father. The first person to capture this phenomenon clearly was the 19th century British polymath Francis Galton. Deeply interested in heredity, he gathered heaps of parent and child heights and compared them, and found a curious regularity. It looked as if the children's generation was being quietly pulled toward the middle, the human average. In the year 1886, Galton nailed this name into his paper's title, Regression Towards Mediocrity. He even read off the size of the return as a number. Only 2/3 of the parents' deviation carries over to the children. The remaining 1/3 returns toward the mean. That's why even the child of tall parents isn't as tall as the parents. At first Galton took this to be a biological force returning the species to mediocrity. But that is the most common misconception. He had already seen the very same pattern earlier, in his sweet peas experiment, even though seeds have no will to become average. Why does this happen? The answer is hidden inside what we call a score. Test scores, flight ratings, height, a season's batting average. Almost every value we measure is the sum of two parts. Skill sticks around stably and barely changes no matter how many times you measure it, while luck, your condition, which questions you happen to draw, shifts from one time to the next. Now the key point. If a value is unusually high, it's one of two things. The skill was outstanding or the luck was exceptionally good. The more extremely high it is, the more likely that good luck lent a hand. But that good luck doesn't follow you the next time. The skill remains, but the luck returns to the mean. So the next value comes down toward the mean below that first extreme. It's simply that there's no reason for luck to strike twice in a row. Let's switch to dice. Whoever tops the total likely has a high base score and rolled a 6 on top of it. The base score stays the same, but there's no reason to roll another 6. Since the average is 3.5, the total comes back down. The same goes for last place. Rotten luck doesn't repeat either, so next time they climb back up. Words alone are hard to trust, so let's draw the very picture Galton saw. 5,000 imaginary students take the same test twice. Each score is skill plus a fresh draw of luck each time. If it were pure skill, every dot would sit on the gray diagonal, but with luck mixed in, they scatter around it. Watch the orange regression line. For a given first test score, it connects the average second test score, and it lies noticeably flatter than the diagonal. For the students at the far right who scored above 90 on the first test, their second test average falls well short of 90, down toward 70. It's not that individuals get dragged toward the mean. It's just that those who luckily rose to the top on the first test didn't enjoy that luck on the second. And the slope of this regression line is exactly the correlation between the two tests. Here it's 0.6. The stage where regression truly fools us is when we select the extremes and then measure again. The world is always selecting the extremes. It gives the top scorer a prize and puts the top returning fund on the cover. The trouble is, from a single measurement there's no way to tell whether that extreme came from skill or from luck. The group that aced the first test mixes genuine top performers with ordinary students who got lucky, yet we lump them together as one elite group. When the lucky students return to their usual level on the next test, the group average is bound to fall, even though all we did was pick out the extremes. The health checkup hits closest to home. Pick only the people whose blood pressure read unusually high, remeasure a few days later, and the average has dropped with no medication at all. This is exactly the trap the flight instructor fell into. Praise went to the upper extreme, scolding to the lower extreme, and on the next flight they simply returned to their usual level. Let's prove it with code, not words. We'll build the flight instructor's illusion on a computer ourselves. We create 4,000 pilots. Each has a fixed skill and every flight score is that skill plus that day's luck. Crucially, this experiment includes not a single grain of any effect from praise or scolding. Then we act like the instructor. We label the top performers praised and the bottom scolded. And look at each group's next flight. Look at the results. The praised group's next flight dropped by 0.84 points on average, while the scolded group rose by 0.77 points. Nowhere in the code is there a rule that praise makes you worse. And yet the exact pattern the instructor saw is reproduced perfectly. An instructor holding only this data would stay convinced that punishment is the cure and praise the poison, and would badger perfectly fine trainees for a lifetime. This is why regression to the mean is so frightening. For an action that has no effect at all, it manufactures clear evidence of an effect. Kahneman summed up that day's realization like this. So does regression always happen with the same strength? There's exactly one dial that sets its size. How large a share luck holds in the outcome. For something that's almost all skill and almost no luck, like a 100-meter dash time, there's almost no regression. Whoever's fast stays fast next time. Statistics measures this share of skill with a single number between -1 and 1. The correlation. The one formula worth memorizing in this piece is this. Once you standardize the scores, the prediction for the next value equals this times distance from the mean multiplied by the correlation. Since the correlation is less than 1, the prediction is always closer to the mean than this times value. That is exactly regression. So the amount of regression is roughly proportional to 1 minus r, the correlation. The larger luck share, the harder you get pulled in. Now let's turn this dial in pictures. Here are the scatter plots when the correlation is 0, 0.3, 0.6, and 0.9. The gray diagonal stays the same throughout, but the orange regression line lies flatter and flatter as the correlation shrinks. At a correlation of 0.9, the regression line hugs the diagonal, so regression is slight. At 0, it becomes perfectly horizontal. This picture also explains why regression is especially dramatic in certain domains. The larger luck share in an activity, the weaker the correlation. Conversely, a stable trait like height has a high correlation, so regression is weak. But it isn't 0, which is how Galton caught even that faint regression. Now that we're armed, let's tour the myths the world invented by mistaking regression for causation. The common structure is always the same. Pick out an extreme, watch it naturally return to the mean, then pin a plausible cause on that change. First, the magazine cover jinx. The story goes that an athlete who lands on the cover of Sports Illustrated slumps right afterward. But to make the cover, you have to be coming off an unrealistically great stretch. The ordinary return after that peak isn't a jinx, it's regression. To be fair, though, football has frequent injuries, so there are factors that regression alone doesn't fully explain. Second, the sophomore slump, the rookie of the year who, unbelievably, falters the following year. Winning rookie of the year took luck on your side that first season, and the next season, as that luck drops out, you come down toward the mean. Third, the miracles of new drugs and folk remedies. People usually see a doctor or take medicine when their symptoms are at their worst. After that worst moment, things usually improve no matter what you do. So even a useless treatment easily earns testimonials that it cured them. In fact, in one clinical trial on agitation in Alzheimer's patients, neither the drug nor behavioral therapy differed from placebo. In the post-hoc analysis, the improvement in the placebo group matched what regression to the mean alone predicted. This is the core reason medicine insists on a randomized control group. Only by comparing against a control left alone can you separate true drug efficacy from regression. Fourth, the myths of funds and management. In 1933, Seckers tracked hundreds of companies and drew an intriguing conclusion. He claimed competition drags every company down toward mediocrity. Then the statistician Hotelling delivered a sharp rebuke. Such a study, he jabbed, is no different from lining up elephants in rows and columns to prove the multiplication table. Finally, there's one trap you must keep separate. Regression to the mean is not the gambler's fallacy. The gambler's fallacy is the delusion that since red has come up 5 times, black is due this time. Roulette has no memory of the past, so it's a clear error. Regression, by contrast, is a real fact that appears when you pick an extreme out of a Lucklace measurement and then measure again. It's about reading what an already observed extreme really was. Now the finale. Take today's truth home in a single sentence. Luck does not repeat. Regression isn't hard. An extreme outcome usually had luck lending a hand, and that luck doesn't follow along next time. That's all. The hard part is remembering this, because the brain prefers a dramatic story to a flat explanation. So the next time you see some extreme performance or crash, pause and be skeptical before you build a story of cause and effect. Especially right after something hits a peak, the drop that follows is more likely statistical gravity than failure. And the flight instructor's story hides a warm lesson too. Praise does not ruin people. If the score seemed to drop after praise, it wasn't because of the praise, it was because that moment was, from the start, a peak that luck had also favored. If anything, psychological research has said close to the opposite. Encouraging beats berating when it comes to learning. So go ahead and praise those who did well all you like. There's no reason to let statistics rob you of that joy too. Let's close with one rule to remember. Whenever you pick out an extreme and then measure again, subtract regression first, before you credit anything you did. If you enjoyed today's journey, support us with a subscribe and a like. See you at ELLSLAB for the next Odyssey.